Welcome to my tutorial video how to use a DMM. In this video I will not only explain how to use a DMM, I will first explain what it actually is, why you need one, which different kinds of DMMs or multimeters there are, what you would do with them, and finally how you safely and correctly measure whatever you need for your project. So first let's start with what actually is a DMM. DMM is short for Digital Multimeter. So first of all, a DMM is a meter, which means you use it for measuring things. You might have already at home a length meter, or called a ruler. You might have a temperature meter or thermometer measuring temperatures. You might have a scale or a weight meter, for example like this one, where you would measure how much your luggage weight. You might have even an electrical one like this one for measuring current. You might have such a very old one used for measuring voltage, current and resistance. Or maybe you own already some of these small USB meters which are used to measure how much a USB device takes as current. So a meter is something which you use for measuring certain physical values or units like weight, size, voltage, temperature, whatever you need. A multimeter is a meter which can be used to measure multiple of these units. So not only like length or so, but for example like this one here, it can measure current and voltage, whatever you need for your project. Or like this one here, which measures also voltage and current for USB. Usually when you are talking about a multimeter, it also implies that it's kind of a universal device, so it's not only for a very special function, but can be used whenever you need to measure the certain physical value. Like for example, this multimeter here has 6 ranges for current, has 3 ranges for voltage, 1 for resistance, and it can also be switched on the backside between DC and AC voltage or current. So that's why it's called really a multimeter, because it can do multiple things in multiple ranges for all of your measuring needs, because they might be varying. In contrast, this one here measures voltage and current, but for each of them it just has one specific range, like 20 to 5 volts for voltage, and it can measure in the 1 to 2 amp range for current. So it's not really a multimeter, it's a very specialized device, even though it would measure multiple units. And then we have the distinction between analog and digital meters. So these both here are analog ones. You see, you have a scale, you have a needle here, or you have the needle here, and it's analog. The needle can move to any point on this scale, and you need to read which one you have. In contrast, this temperature meter here is digital. It shows you only certain values. It cannot tell you that there are 26.43 or 4 degrees Celsius here. Something that this one here would actually show. It would be a thermometer. So that's the big distinction, and that's why when we are talking about a DMM, we are always talking about a digital multimeter, which would be something like this kind here, or more specific, something like this multimeter here, which measures even more different values. So our next question would be, why do we actually want to measure things? Why can't we just build our circuit according to a schematic, power it on, and hope that everything works, and if not, just try and find out what we actually did wrong? So there are three reasons why you want to measure certain values like voltage, current, or even length when you build something. First is, sometimes you just need to prepare something to a certain specification. You want to examine how certain values in your circuit or in the thing that you are building, which value they actually have, and sometimes you just need to verify whether whatever you build behaves as it should. So for preparation, when we are talking about electronic circuits, one of the things that we usually care for is supply voltage. So think about having a battery powered system where you have a voltage range from, say, if it takes 2 AA cells, somewhere between 2 and 3 volts. So you want to make sure that when you try it out that you do not power it, let's say, by 10 volts, because it might not even survive that. You also want to make sure that you do not power it with, let's say, just 1 volt, because it will not function correctly. So that's what you need for preparing. If you build something physical, typically you cut something to a length or to a specific angle. So you also need to make sure you measure first before you take your cut, so you prepare whatever you are doing. Next one is you examine, you investigate your circuit. Again, if you take your battery powered device, you are probably interested in how much current it actually needs, so you know how long your battery will live. So you power your device on and you measure which amount of current it needs, so you know the power consumption, and that's what you examine. And sometimes you verify, for example, when you build a circuit which should generate a specific voltage or a specific waveform, then you actually need to verify that the voltage is what it is supposed to be and not something else. So these are the 3 steps. So also for examination, if your circuit does not really work for some reason, maybe you soldered something wrong or just had a wrong idea of how your circuit should work, you need to examine what part of your circuit does not work. Are the inputs at an incorrect value? Did you solder something in incorrectly and you have too high current in some places, something like that. One of the distinctions when you are talking about different kinds of multimeters is whether it's an analog or a digital multimeter, a digital measurement instrument. I have here 2 instruments showing both the same current, roughly 90 microamperes. And you can see that the distinction is that for the analog one we have here a scale, we have a needle, and we need to look exactly at this point for the needle to read the actual value, whereas for the digital one we can directly read a very precise value for this one. But one of the advantages for the analog ones is that it's much easier to see the rough value of where the value actually is. So when I reduce this current here, I can very easy, even from, let's say, 2 meters away, recognize, yeah, okay, that's a low value. It's at the beginning of the scale instead of being at the end of the scale. If you want to do that for the digital one, you actually read the value, which might take a bit more time, and this might be important because for the analog ones, even if you have 10 meters there, you can even see, okay, they all show the same value, or just one of them is off and can react to that one. The advantages for the digital meters are they are usually way more precise. This meter here is accurate to 1.5%. The digital one here is accurate to even better than 0.1% of its value. They are also easier to read because here for the scale you really need to make sure that you look exactly directly perpendicular to the scale, because otherwise you might get a parallax error where you read this value from a slight angle and might read it differently. So at least as long as you want to get a very precise reading. More expensive ones even have a mirror on their scale, so you can exactly check that you are looking at it in the correct angle. Usually the digital meters, they are easy to read, there is no mistake. I know exactly what the current here is. No, I can probably even read it from a bigger distance to get the actual value without making any mistake there. Usually they are much more precise from just their technical specification. I guess that the best analog meters are around 1%. Maybe you get some better ones, but for digital ones You even get meters that are 10 or even 100 times more precise than the one I am having here. So let's have a look at the different kinds of digital multimeters that we have. When someone talks about a DMM, usually we are talking about one of these handheld universal multimeter used for measuring voltage, current, resistance, maybe capacitance, frequency, and temperature. But these are not the only ones that we have. We also have multimeters that can be placed on a bench. They are quite a lot bigger, are mains powered, used for measuring the same stuff but for different purposes. But there are also are other kinds of, let's say, multimeters or digital meters that you might have. Over here I have LCR meter, which can be used to measure inductance, capacitance, frequency. I have here a specialized frequency count and signal generator. A very special one is an oscilloscope. That's not really a multimeter because it shows you values over time as a curve here, but sometimes that's very handy. So when we are talking about actual multimeters usable for electronics work, used for the general purpose stuff, the big distinction is between a handheld multimeter and a bench multimeter. Handheld multimeters, as their name implies, can be held in your hand. They can be moved around, placed wherever you need them. You can take them outside. So these are the ones that you take to wherever you need to measure something. They are quite ruggedized, sturdy, except when you have smaller ones. They are even smaller ones than this old one here. They basically fit in your pocket. They are not as sturdy as this Agilent one here. But usually they are quite robust because they will be used in various conditions. They might be might fall from your desk. You might hit them with a screwdriver or even with a soldering iron. They will be used outside in bright sunshine, as well as if there is temperatures below freezing. So that's why they are quite rugged here. I would even guess you can take this one, throw it at the colleague who just messed up here with your circuit, if you want to, and it probably will survive that. And on the other hand, you have these meters here that are meant to be placed on a desk, even the whole stack here on my bench. So they are quite a lot bigger. They are mains powered, so you can run them basically all day long. You will not eat up their batteries. They are designed to be stackable on top of each other, so you can take this one, put another one on top of it, like I did with the ones above here, where I stacked basically 3 instruments on top of each other. So that's what they are used for. So basically their size dictates what you can do with them. You see here most of the handheld multimeters, they have a range switch that can be just rotated. In contrast, many of the bench multimeters just have buttons for all of the selections that you need to do. And then you have a number of additional UI elements to switch between different functions. Like, for example, you can select a fixed range here with a button. You can do relative measurements. You can switch on hold or max-min measurements. And basically that's it. There usually is not more on user interface on such multimeter. This one here even has fewer buttons, and if you have a simpler one, it might even have no buttons at all. You just have a range switch here. In contrast, the multimeter that you have on a bench, there you have much more real estate for placing elements on it. So you have your selection buttons here, you have some additional configuration here, and you have even more functionality here, and that's because you can have a bigger screen because you just have a bigger instrument, and you can use it to add more functionality, which we will come to later. And that's sometimes very helpful because that might be what you need. On the other hand, you cannot take this one and take it outside for measurement. Maybe you can if you want to, but it's not really practical. You really do this only when you really need to, otherwise you just prefer one of these over here. One of the other differences between handheld and bench multimeters is that usually a bench multimeter comes with much more connectivity. While this meter here in the back has an infrared port which you could connect to your computer to read out measurements here or take them live, so you can actually do kind of data logging. It's quite awkward, and since it runs on a battery, it's not something where you would say, yeah, just let it run for a week or so to take some measurements every second. This instrument here has a serial port. It has a USB port on the front where you can store values on a USB stick. It also has an additional USB and an Ethernet port in the back where you can actually connect it to your computer and control, even not just read measurements, but you can even switch ranges, configure whatever you can do here, and do really long-term measurements. And it's way more practical to do this with a bench multimeter than to do it with such an handheld one, where you might actually fear that you just move it on a desk and the infrared cable will come loose here. But if you need it, it's nice you have it there. But the big selling point for the bench multimeters, in addition to being main sport and having more functionality, really is this connectivity which you can use to do much more interesting measurements. For example, you can also take multiple of these instruments, so you can run multiple measurements in parallel for different values, which sometimes is just what you need. So what do you actually measure with a multimeter, and what's the important part about measurement? What are the things that you need to know? So basically all of these meters that I have here, 3 handheld ones and the bench multimeter over here, can measure more or less the same things. They measure voltage, they measure current, they measure resistance, capacitance, temperature. Same here, voltage, resistance, capacitance. Okay, frequency, they can both do frequency and current over here. This one can not do temperature, this one here can do temperature, and it also has a mode where it can contactlessly find magnetic or electric fields over here. Similar for the bench multimeter: voltage, current, resistance, capacitance, frequency and temperature. So they are quite equal here. What they are differing in is basically in accuracy and precision. So precision means basically how much digits do you have for measurement. This one here has 4 digits. These two here have 5 digits. This also here have 5 digits that it will show you. In the terminology, these are 4.5 digit multimeters. This one goes to 50,000. This one goes to 22,000. This one here also goes to 60,000, and this one here goes just to 6,000. So these are the different values that you have. So that means how precise can you read the actual value, where you see, yeah, okay, this one here is just less precise. It has just 1 digit less than the other ones. And then the second thing that you need to know, and that's something that you need to look up for each of these meters, is their accuracy, which means not just how many digits do you have, but you want to know, if you read a value here, how much could it, in worst case, differ from the actual value that you want to measure. So if you measure 1 volt, maybe they will show 1 volt, and if they do, you want to know, okay, what's the highest and the lowest voltage that could actually be that I'm measuring here at these sockets. I already mentioned that 0.1%, I remember that analog meter here has a precision of an accuracy of 1.5%, which means that when it would show here this 100 microamps here, right at the full scale of the range, it might even be just 99 microamps, and it would be still within specification here. These meters here are way more precise. So this multimeter here has a base precision of 0.1% for its voltage range. Usually voltages are the most accurate ranges, because a meter basically just measures voltage internally, and any other thing, a unit that you measure here, like current or resistance, will be converted internally to the voltage. So this has an accuracy of 0.1%, which means that when you measure 1 volt, it might be off by 1 millivolt. That's not too much. This one here is accurate to 0.025%, and this one here to 0.02%. So this one is 4 times more accurate than the Unity one here, and this one is even 5 times more accurate. So that's basically the most important distinction when you want to know, okay, how well can you measure your circuit and be confident that you measure the right value. Usually the more expensive the meter is, the more precise it is, the more accurate it is. But you actually need to look up in the manual on the data sheet how good the accuracy is for a certain range. So for example, AC voltage usually is quite a bit worse than DC voltage. Current is a bit less precise than voltage as well. Resistance usually is quite precise. Capacitance usually is just precise to maybe 1 or 2%. So it's way less accurate than when you're just measuring voltages. So you need to look it up, which of the ranges is how precise for your measurements. Some of the more, let's say, specialized functions that you have are diode measurements and resistance. These usually are just a special kind of resistance measurements. So when you switch to the resistance mode, you get told, yeah, okay, you have an open circuit here. So it tells you, yeah, kind of an overload or overrange. But you can switch to continuity mode. You usually see this by such a buzzer symbol over here, which is a special resistance mode where the meter usually switches to its lowest resistance range, and whenever the resistance measured is below a certain value, the meter will beep. So let's plug in some probes here. So, and now here you see it measures way less than 1 ohm and it beeps. The important property for a meter is here how fast it actually reacts when your probes have continuity, meaning that you have a very low resistance between them, and whether it's latched, which means it should not just make its beep when it measures this voltage, but it should take at least, let's say, 1/10 of a second or so for the sound. So you can see here, when I'm fast enough, you will not get a beep here. Another one of the special ranges here for the resistance mode usually is the diode measurements, which can be used to measure the voltage across a diode. So when you want to verify whether a diode is working correctly, you switch to this mode. You will have a constant current flowing through the diode, similar to the resistance. But instead of showing you the calculated resistance, you just get the voltage across the diode here. If I short this out, yeah, you get 0 volts, of course. what's interesting here, and that's something that you need to look up in the manual, is not just how much current is flowing through the diode, but actually how much voltage the meter can output on its terminals here for this diode. For a normal one, that's usually not an issue, but if you want to measure LEDs, you want to have a voltage that's at least 3 or 4 volts high, so the LED actually lights up and you can find out whether it's still working or not. A white LED usually has a voltage of about 3.6 volts, so it would be nice if your meter can actually place such a high voltage on it. This one here cannot. I think the HLN here can do that. So when you want to measure like white LEDs, this meter would be much better suited. Another specification you really should look up for your meter, as long as it's specified in its datasheet, is when you switch to a current range, like this one here, 4 milliamps, each meter has a so-called burden voltage, and that's the voltage that will be dropped by this meter as soon as you measure current. So when I place this over here and I have a current flowing through this meter, there will be a certain voltage that will be dropped over the resistor internally to the multimeter. And you need to know how big this voltage is, because if it is too high, your circuit actually might stop working. I mentioned in the beginning, when you measure like current consumption of a battery powered system, you might power your system by, let's say, 2.5 volts. That's very reasonable for 2 AA batteries. And then you find, yeah, okay, my circuit actually kind of stops working or does not work properly. And when you then look up the burden voltage, then you might see that your device draws like 1 milliamp or maybe 10 milliamps or something like that. And then you see, oh, in this current range, the voltage drop for this meter is maybe 1 volt, which means from your battery voltage of 2.5 volts, only 1.5 volts actually end up at the device that you are currently testing, and this just might not be enough. So that's something that's important to look up. Usually it's not that high, like a volt, but half a volt might be easily happen, depending on the actual range that you are using here. So that's something that you really need to look up. Another important specification of multimeters is related to safety. Not always will you do what you intend to do. Maybe you place the meters at the wrong place in your circuit. Maybe your circuit has a way too high voltage. Maybe you misconfigure your meter. The first thing is, would the multimeter survive whatever you do to it without losing its specification, so its accuracy? And the second thing is, does the meter survive well enough not to kill you? For the first thing, for the first input protection, you look at what's printed here across the sockets. So this meter tells you, yeah, okay, this socket here is fused for 10 amps, so that's what you can do here. This one is 440 milliamps, and over this socket here you can have at most 1000 volts. So since this one here is used for temperature measurements, for resistance measurements, this meter should survive if you try to measure a resistor and for some reason you have mains voltage on this resistor. It might not show the correct value for this resistor, but the meter will survive, and when you remove it from your circuit, wait a bit for the input protection to cool down. It should be fine afterwards and still be within its specification. This meter here basically has the same information. The big difference here is that this one tells you it's fused here to 250 volts maximum in its current ranges, in contrast to what it tells you here for this range. So you need to be a bit more careful here. The other thing that this meter here has as a functionality is that when you place your cable into the amp socket while still being in a voltage range, so it will not happen when I am doing this here, This meter will beep on you and tell you it's a very bad idea to try to measure voltage when you have your measurement leads plugged into the amp socket, because it's basically a short circuit, and in the best case it will just blow the fuses. In the worst case the meter might explode on you. That's why it's warning you. These two here cannot do that, so you need to be way more careful with these. The second important part is how much misuse can these meters accept until they might kill you. This is where these CAT ratings here come into play. And basically a CAT rating is an information about how much energy might be available in your circuit that might be discharged into the multimeter. So CAT 1 is everything that's not mains powered and on low voltage, like let's say it's battery powered. Maybe not a car battery that has quite a high amount of energy, or lithium ion batteries, but let's say a normal AA cell will not cause any problems. CAT 2 means anything that's, let's say, a standard appliance, so anything that you plug into a socket has a power supply. Even if you measure on the main side of such an appliance, you are protected by your building installation, like circuit breaker and things like that. So you are usually with these meters here quite safe. CAT 3 means anything in your building installation, so anything that's basically wires that in your walls, switches, the circuit breaker board, things like that. And CAT 4 means anything that's basically before your circuit breaker board, so anything that really is outside of your house, that's basically unprotected. So your house, at least here in Germany, anything here in my sockets here have circuit breakers with 10 or 16 amps. The house has a circuit breaker with 63 amps, and as soon as I'm leaving it, basically there is no protection anymore. And this meter says, okay, I'm basically safe as long as I'm inside of my house up until a regular measurement voltage of 1000 volts. That's not the highest voltage which will survive. When you look it up, the specification for CAT 3 says, if I remember correctly, if you measure 1000 volts, the highest voltage this meter should survive is 6000 volts, which is quite a lot of energy. And this meter basically might not survive if it sees a voltage of 6000 volts on such an installation, but it will not explode in your hand. It probably will not survive internally, so you will need a new meter then, but it will not kill you. This meter here basically says the same thing. CAT 3 1000 volts, CAT 4 600 volts. I know this one is too cheap to reliably protect me. I would not trust this with, maybe not even with mains installation, when I'm measuring like in a socket here or so. I will always use this one here. This is much more rugged, has much more input protection. It will survive more when I'm doing something wrong without losing its precision, and it will also do not kill me. You also need to be careful and really look at the specifications. This bench meter here tells you it can measure up to 1000 volts. Okay, that's important. It has this additional information here that the ground terminal cannot be more than 500 volts away from the actual protection or earth protection of this meter, which you usually should not reach, but it might happen. This could kill this meter. And the second important thing is, and that's not mentioned here, is that in AC mode it's still 1000 volt maximum, which means that you cannot measure more than around 700 volt AC voltage, because the peak of such a voltage will be 1000 volt. That's the difference to these ones here. They still reach a specification of 1000 volt even in AC mode, so you can measure 1000 volt AC which in reality has a much higher peak voltage. This meter here cannot do that. So that's important to look at. Also to notice here, this one is also fused only with 250 volt AC, so the current ranges are also only for 250 volts. So that's also important to know. This one here, as far as I remember, has a fuse really rated for 1000 volt inside for these ranges. So before we start talking about actually measuring anything in our circuits, we need to talk about probes, because without probes your multimeter will be very useless. In the end, what you want to do is you have your circuit board like this evaluation board here, and for some reason you want to measure voltages or current on this, and you somehow need to connect your multimeter to your circuit board. Usually any multimeter that you buy comes with a set of simple probes like these ones here. Maybe you get some accessories for them, but basically that's what you get for them. You see, these are needle type probes here, so they have this more or less sharp tip here, which is intended to be attached to the circuit here. When you want to evaluate how good these probes are, you basically look at three things. First is the quality of the tips itself, then you look at the quality of the cables, and then you look at their resistance. As a comparison, I have these probes here that came with my Accuray handheld multimeter, which are of a bit higher quality than these ones here. So when you look at the tips here, these are needle types tips here, so they should be quite sharp, which is useful because when these probes are not really sharp, you will not be able to pierce through any oxidation that might be on your circuit board. So this one here is nice and shiny and clean, but when it's something that has been, let's say, on the outside or is several years old, you probably have oxidized contacts here, and when your probe tips are not sharp enough, you will not be able to pierce through this insulation and you cannot really measure anything. Second, you look at the quality of the cables itself. So they should be with silicon insulation, because that's much more temperature resistant, and silicon is also much softer than PVC wires. PVC isolation, these probes here are PVC, they are quite soft, that's quite nice, but PVC means they are rated for about 100 degrees Celsius, whereas these cables here are rated for 150 degrees. That's usually not an issue, but when you are working on a bench which might be crowded, then it just can happen that you place your cables somewhere and your soldering iron gets in the way and starts burning down your cables, and that's not what you want, because they might be expensive, it does not smell that good, and if you're unlucky you kill something with that. And the last thing that you want to look at is total resistance, which means the resistance from basically the tip of the probe to these connectors here. That's important for several reasons. One is if the resistance of the tip is too high, you probably do not get good contact. You might measure wrong values, especially for resistance, but also for other types. And when there are some coating or oxidation here on these tips, you usually cannot work properly with them. Also, when the cables itself have a higher resistance, they are not of a good quality, and whenever you measure currents or resistance, you probably will read quite some wrong values, because they introduce additional resistance into the circuit. Also, you can look at how well they are suited to be held in your hands. So these are more or less equivalent. They have this nice sleeve here, so you do not accidentally touch your circuit or any higher voltage that you are working with. For the Accuray ones, they are, for my opinion, they are a bit too long, so they are always a bit of a hassle to hold, because the cable somehow always gets in the way. So I would prefer the shorter ones. What's nice about this one here is that you can remove the tip and add something else here. So when you have additional accessories, you can just use the same cables and you just change this one here. So you just change the tip. But apart from that, I think handling wise, these are better because they are just shorter. If you think that your multimeter comes with a set of probes that's not really so nice, or if you're uncomfortable with it, go ahead, buy new ones. In the United States, I think Pomona has a good reputation. For Europe or Germany, I have made good experiences with SKS Hirschmann. Mostly all of the probes that I bought recently are from this brand. I will show some of them later. It usually pays off to get a good set of probe. They last a lifetime. I have never ever broken a good set of cables. So they are usually very well worth your money, and they just reduce the number of issues that you might have when you measure something wrong. It's always helpful if you know, okay, it's not the cables, it's something else. So, needle type probes, they are intended to be placed on your circuit board for measurement basically like that. So where you use the black one to find the ground point on your circuit, and then you use the red one to measure your actual voltage or current or whatever. But this has the problem that you need already two hands to place the probes on the circuit board here. Then maybe you need a third hand to actually operate the board. So for example, you might want to change this trim port over here to change some value. You also need to look at your probes so they are not moving and stay in their place, and then you also need to read the value. So that's usually not what you want to do. Also, when you are not measuring on a circuit board like this one here, but measuring on cables, these probes here are not really well suited for that. So you need something that you can really clamp on, that stays in place, so you can concentrate on your actual measurements. The first variation of that are the so-called crocodile clamps, like this here. So yeah, they look like a crocodile, and they will bite into whatever you have as a wire and give contact there. You should never ever use these ones here, because they are all metal, which just means that whatever you do, you will introduce a short somewhere and will break things or measure wrong values, straight, short, whatever. So you use some of these isolated probes like these ones here. They actually came with the multimeters. I think that's the Agilent one here, or vice versa, I don't remember actually. They are fully isolated here, so whenever you touch them, you know that you will not create any short. But both require quite substantial force to be opened, so they are not easy to operate. I don't really like them. They are also quite big. For the Agilent ones, when you attach them to the probe, they also get quite long over here, so you need quite a lot of room in your circuit board or on your circuit to use them. Hence, I prefer things like these probes here. These are actually Hirschmann ones. They are rather small. They give good contact over here. They held quite well to any cable. You can them use either that way, or you can attach them this way here, so the cable goes in from the front. They will still give contact. They are isolated. They are not so big. They are very, very nice. If you have beefier cables where you need to transfer higher current, you probably want to use one of these here. They are really big and sturdy. Are still easy to operate, but they really give good contact. I think these ones here, even they can connect. You can connect them to a fixed cable if you want to, but I prefer banana plugs for them. The second kind of probes that you can use are clamp-on probes, like these ones here. So they open up when you press them here, and then you connect them either through your wire if you want to, and they give contact, or you connect them to like a pin header over here. and then they will just stay in place. These ones here are rather big. They are intended for bigger cables, or when you work with higher voltages because you have quite some distance to your point for measurement. There are also much smaller ones, like these ones here. They are of hook type, so you just hook them over your cable or your connector like this one. They stay in place, they don't take too much space, so that's really nice. And these also come in much smaller variants, like these ones here, and they are, you can see that they are intended to be actually connected to even circuits, to like ICs, or directly to probes like this one here, where you do not have so much space. I have these nice Hirschmann ones. They are even a bit finer, and I would actually trust them to connect, let's say, an SRIC package with 1.27 millimeters of pin pitch. I think they will work quite well for that. Otherwise, for anything, I usually prefer this style here because they just stay in place much better. Sometimes it's also useful to create some adapters. So for example, whenever I want to connect something, because I want to measure with these terminal blocks, I have here banana plug, banana socket, just with some copper wire, which I can just place into here, screw it into place, and I connect any measurement cable to it. So that's something that's very helpful, and it sometimes really pays off to create your own connectors. Another style I have are these ones here. These are just 2 pin headers soldered to nice silicon wire, and it's very useful when you work with breadboard because you can just place your probes into the breadboard. That's very, very useful. When you buy cables and connectors, or even especially if you create your own ones, be aware, do not use cheap connectors. These ones here I think are Chinese ones, where I think like 10 or 20 connectors cost like 10 euros or something like that, or even cheaper. They work, but they will come loose. They not always give good contact here. So it pays off to use better ones, like I think these ones here are something that's called Pomona style. I think they are using these quite often. Or you can use nicer ones like this one here. If you want to build your own laboratory and say, yeah, okay, I'm buying stuff that I want to use for many years, it might be useful to actually buy a complete set of cables, like these Hirschmann ones here. They are really nice. I think they are rated for 16 amps. Quite sturdy, stackable, come in different wire length. I think these are 0.5 meter, the other ones I am using are 1 meter. Depends on your bench and how much space you have, which lengths you probably need and which are useful for you. But it really pays off to have a good set of cables. So I already mentioned that one of the important parts about measurement is actually connecting your multimeter to your circuit under test. So when you have a board like this voltage converter here, and you want to measure, for example, how the output voltage changes when you place load on it, or whether it's actually accurate, you have either these terminal blocks here, where you can screw on your cables, or you can try to place directly on the pins. I already mentioned that when you use these needle type probes, you need to hold both of them, need to concentrate on looking at that you place them correctly, which makes it difficult. So what you actually want to do is, at least your ground pin should be connected, or your ground cable should be connected to a fixed place on your board, so you don't need to hold it in place, so you can concentrate on probing the other wire. On evaluation boards like these, it's common practice to actually have like these test hooks here, which you can use to easily connect such hook style probe. If you have a screw-on connector, you can use that one. But that's something that you very often have. Sometimes you have like these headers here for connections. They are intended more for oscilloscope probes. But whenever you create your own circuit on a PCB or on a perf board, you should always try to include, at least for the important signals, some of such test hooks. Sometimes I just connect wires. If you have a PCB like this one here, which has some connectors, this one is for programming, this is a serial port, this is an extension header. You need to go looking, okay, which of these signals are actually important ones. Like, for example, I happen to know that there is a ground connection on this programming header here, so I connect my probe to this one. At least this board, or the designers of this board, were nice because they actually added all of these small wires here around this big chip. So any pin from this microcontroller here is routed to one of these wires, which you then can use for actually probing. So you can place your probe there, and it will stay in place. In contrast to when you do not have any test points here, you really need to find the right pin, place your probe there, try to hold it in place, and then try to read your multimeter to get your measurement. So that's very inconvenient. So if you want to do that, it would be better to actually try to solder a wire to exactly this pin, or find some nearby component where you can solder a wire onto. But I like the solution with these wires here. They really work great as probing points. When you probe your circuit, the best thing that you can do is to connect your probes in advance while the circuit is still powered off. Take your time, connect it to wherever you want to, and then turn it on. Because it means you do not work your way through this circuit with something that's metallic. Because if you probe here, for example, and you somehow lose contact and you go to the next one, then you might create a short between these two pins. This might just mean you read something wrong and are confused because it's not what you expect. But in the worst case, you actually connect something to plus 5 volt and it will kill your IC. It's especially important if you're working with higher voltages, so for anything that's mains powered, if you really want to work on that, really power it off, connect your probes, and only then turn it off. Best thing you can do is actually pull the plug and only put it back to the socket when you are actually ready to measure and have connected everything, so you don't need to touch it while working on it. Because that's usually the easiest way to kill your circuit and maybe yourself when you just accidentally touch something that you should not touch. So let's talk about measuring voltages. So I have this circuit board here, which is intended as an evaluation for this microcontroller here, and there's a demo program on it. And one of the functions is that it has an analog to digital converter, and it changes its value whenever I change the string potentiometer. Here you can see that there are values from 0 bis, actually should be 1024 because it's a 10-bit converter. And we can see, okay, this changes here. So one thing that we might want to do is to check, okay, whenever I place this right at 50%, it does not read half of the value. It reads 460, but it should be 512. So maybe you want to check, okay, is this something that's wrong with the analog to digital converter, or is the string potentiometer here just not accurate enough to do that? So first thing to do is reconnect our voltmeter, our DMM. So the important part about voltages is whenever you want to measure voltages, you connect your voltmeter in parallel to the voltage that you want to measure. So for example, I have drawn here a very simple circuit, a transistor driving LED, and its base voltage is changed also by a trim pot. And if you want to measure the voltage on a trim pot, you connect the voltmeter in parallel to the place on the trim port where you want to measure. So that's how you connect your voltmeter there. If you want to measure current, you do it differently. That's something that we'll see in the next episode. What's important to know is that each voltmeter appears as a resistor. Usually a voltmeter has a very high resistance of 10 megohms. But if your resistor here is also, let's say, 10 mega ohms, then it would mean that whenever I connect this one in parallel, it actually reads half the value, because 10 parallel of 10 just means 5 mega ohms. So that's something that you need to be aware when you work with especially low current circuits. Usually it does not really matter. This voltmeter here actually has an even higher input resistance if you want to, but usually you stay with the 10 meg ohms. That's quite of a nice compromise between resistance that's high enough to not really influence the circuit, but it's not so high that you create or get too much noise, because if the higher the input resistance, the more noise you can get here. So that's how you connect your voltmeter. So I use these small probes here. I turn off my circuit. So it's off. I connect this probe here to one pin of my trim pot. I connect this connector here to the other side of the trim pot. Maybe you can better, so I just connect this here. This works because this trim pot here is placed some millimeters above the PCB. If it's really down there, I would probably have soldered some wires on the back to the trim pot, so you can easily connect to it. So we turn on, and we already can read some voltage. So what we now would do is first switch this to the same measurement, and we check what's the actual voltage range here. So turn it right to there. Okay, I can read 0 volts. I can turn it to the maximum value. That's nearly 3.3 volt, which means half of that is 1.65 volts. So that should be a 50% reading. And try to get it at 50%. And yeah, we can see, okay, it's just 1.5 volt, which means that this trim potentiometer here is not really linear. Where it should be at 50%, it's below that. So that's the reason this one is not reading correctly, and we can check if I can get it to 1.65 volt. Yeah, it's at 513, so probably the ADC in this chip is more or less accurate here. So what else do we need about measurement? One thing that you might already have seen is that the multimeter here does auto ranging. It says here auto, and it's in the 6 volt range. If I go lower, then it will go to the 600 millivolt range. If I could go above 6 volt, then it would switch to the 60 volt range. So that's usually very handy, because it always means you get the best position for your actual value. But it might also have some drawbacks, because, for example, now I'm reading here a value of 437. That's easy to read. And if I increase that, now I'm reading just 0.8, and I need to know, okay, is this now more than your original value that I had with 400 or less? Because the decimal point here has also changed, and the unit has changed, so it's not always easy to see when your signals change rather fast what the actual value is and which one of these is bigger or smaller. So for that one you would probably switch to a fixed range like 6 volt here. So now it says manual 6 volt, and now when I go lower it stays here, and I can actually see, okay, that's a small value, it's getting bigger, it's getting bigger. And yeah, that's 3 volt, and that's actually more than what I had before. So that's important. For this multimeter also you might have heard it, that when it switches some of these ranges here, that there is a relay switching between the different ranges here, so it's switching the internal resistors. And if you have a signal that varies quite often between these ranges, like around, let's say, 0.5 volt and 1 volt for some reason, then it will always trigger this relay for switching, and it might create some additional wear on that. So it may break earlier than you actually would expect. So that's also a reason to use manual range here. For these handheld multimeters, they usually never have relays in there, so you are fine with using the auto ranging here. But they still have the same issue with recognizing what the actual value is or comparing two values against each other. So that's also something where you might want to switch to a fixed range. Also, you might also see when I change this here that it takes a while after switching the range to actually show the correct value. So for faster changing signals, a fixed range might also be better. So I have shown here that I'm measuring a DC voltage, so it's powered by a DC power supply. If you want to work on AC voltage, like audio signals maybe, or actually mains voltage, you need to switch to AC. There is, depending on your multimeter, different ways to switch between them. For this multimeter, I actually press the volt range button here again, and it switches between AC and DC. For this multimeter here, it actually has two different ranges present. One is for AC, one is for DC. Other handheld multimeters have a separate button for that, so they are switching. What's important to know is that when you measure AC voltage, there will be a so-called AC coupling. So there will be a capacitor between the input jacks and the actual measurement circuit, which means that it will not measure DC voltage. So it's not just that AC means, okay, you can positive or negative voltages. It really measures only AC voltage, and if there is DC voltage, you will not measure that. So you can see just by switching to AC mode, I read 0 voltage, which is not what is actually the voltage on this potentiometer here. There are multimeters that can measure both, and if they do, what they measure is the AC part of the input voltage and the DC part. So you might have a voltage of, let's say, 1 volt DC with an overlay of, let's say, 0.5 volt AC. So the voltage would actually be between 0.5 volt and 1.5 volt. And such a multimeter then can actually show, yeah, this is 1 volt of DC and 0.5 volt of AC. That might come in handy. You just need to know that when you switch to this mode, what it actually means, because this might be a bit confusing what you can actually see there as a value. DC voltage for any multimeter goes into both directions. So if I just switch these, so yes, they are a bit finicky here. So connect this one first, and if it won't let me, okay. Come on. Okay, here you can see, okay, yes, that was actually a negative voltage because I just reversed my probes. So that's also something, it's important to connect your ground lead, that's usually the black one, ready to ground in your circuit, so you know that the other one measures the actual voltage and not something that's in reverse voltage, because there are circuits which work with positive and negative voltages, like operational amplifiers. And if you then swap your wires around, you might be confused by why am I reading a negative voltage when there should be a positive one. Might be that you just swapped your wires. If you know what you're doing, okay, you can ignore it, but usually make sure the black wire from your ground connection, or it's called COM on other multimeters here, that should be connected to the ground connection in your circuit. One feature that sometimes comes in handy is what's called auto hold or data hold. So you have seen here that when I connect, it's not always easy to get good contact on my probe, or especially when you work with these needle type probes and you need to connect them here and you need to concentrate on actually finding the right place where you measure. You do not always have the chance to really read the voltage on your multimeter, and that's where a data hold comes very handy. In many multimeters, that's something where you need to press a button, like here I can press stop and it will stop reading any values. So you can use that one. That's handy when you, for example, want to write down this value or need it later on, then you can just press stop. And this multimeter here has something that's called data hold, which is very nice because it waits until the meter reads a value, and then it holds this value automatically without you pressing any button, even if you remove the probes from your circuit. And it keeps this value until it measures another useful values. For example, I measure this voltage here, I get 1.5 volt. I can remove the probe, I can change to another value, I connect the probe again, and then only then I will get another reading. And it will not go to zero in between. So that's something that's really handy. I have also seen multimeters that kind of have a timer circuit. You press a button and then you have 5 seconds to find your right signal, and then it beeps and then it reads your value. That's kind of in between the automatic function and something that's manual. So that's something that's also quite handy. What you might find on your multimeter are functionalities like minimum and maximum values, which when you turn them off and you take several measurements, or your value changes between several values, then you can afterwards recall what's the highest value, what's the lowest value, what was the average one. Depending on your measurements, that these might come in very handy. So let's try to reconnect these probes here. Yeah, the black one just makes better contact. Looks like I broke something here, so let's switch to another. So that's actually a cheaper one, not as nice, but I hope it works well enough. Yes. So let's turn it on. So one thing that this multimeter here has is called graphing mode, where you can switch between a bar graph, which might be handy, but I should switch to a fixed range, and then I can really easily change here, and I see the bar graph here. I can also switch to a trend mode, where you can see you get the changing values over time. That might be handy when you, for example, have something that reacts to temperature or some outside condition where you can just turn it on, and then you can, for example, place your heat gun on the device and heat it up, and you can look up how the values here actually change. And the last one is called so-called histogram, where you get an histogram of all the different values that you measure here. And you see here the number of measurements now is nearly 100, and I can change here. That's very useful when you have, let's say, a voltage reference where you measure a constant voltage and just want to see, okay, how does it change over time? Are there specific values that appear more often? It should probably be a bell-shaped curve here. I clear here the readings and just keep it there. Then we will see we have readings between 984.38 millivolts and 984.54 millivolts, so they are very close together, and you see these curves here. And now I could, for example, change the temperature here and see, okay, does this curve change and how do the readings actually change? So if you have this on a bench multimeter, that's something that's very, very helpful. So let's go back to my number. What you also have, and usually don't, let's go to this one here. What you can do is you can also do relative measurements, or it's sometimes called zeroing the multimeter. So I could actually go change my potentiometer here to 0, and you see it's not really 0 volts, so there is some voltage here, of course, maybe because this potentiometer is not really perfect. And if I really want to see just the differences in voltages, I can say switch to relative mode, which means it takes the reading the moment I press this button, and then subtracts this value from all of my other measurements. It's not really that useful because the value here is so low. So, but let's turn it off. And let's say my start value is 0.4 volts. I again zero this one out. And if I now turn the potentiometer to its maximum, it's not 3.3 volts as before, but just 2.87. So that's very helpful when you need to compare values against each other. Or say you have some offset in your circuit that you disturbs your reading, you can zero it out. This one is most helpful when you do resistance measurements, because then you can try to remove the effect from all of your wires, but it might also be helpful when you measure voltages. Just be aware you really should turn it off afterwards. Don't forget this because you might read wrong values. On your multimeter, this might be called null here or 0. I have not really seen it called rel mode, but it might, depending on your multimeter, might be called that way. What some meters have is, even in voltage mode, what's called a dual display. That's actually interesting here. I need to. This multimeter is too big. I can switch to dual mode. It doesn't really work because there's nothing connected, but in this mode the meter can actually show voltage here, and it can show the frequency on top of it. So that's something that's very handy if your multimeter can measure this way. And this one here can do it also, but it actually switches between measurement ranges when you do so, which involves clicking this relay or switching via the relays. So that's something I would probably not use on this meter here. I would introduce a second one, but the combination of voltage and frequency might come in very handy if you need it. Also, this multimeter can measure AC and DC, and it would also use the dual display functionality. For a bench multimeter like this one here, you might have additional functionality. One here is called measurement speed. So you can switch between low, medium and high measurement frequency. For this one it really does not change that much, but for many meters, if you change the speed settings, it changes the specification of how accurate it is, and sometimes even how many digits you get. So you might get for a 7-digit multimeter, you might get this only on the lower speed, and when you switch to a higher speed you only get 6 or 5 digits, because the higher speed reading reduces the accuracy. You also can switch on the filter here, which is usually a low pass filter, which can reduce additional noise. So that might be very helpful for this meter. I probably just keep it on always. Something that this meter does not have, but that some multimeters, some handhelds have, is a so-called low C measurement, where the input resistance, I mentioned this in the beginning, of 10 meg gets reduced to something much lower, which then really reduces any noise that might be on your point of measurement. That's usually used by electricians when they measure some voltages or currents, or not for currents but for voltages, especially when they have no signals on the wires. You might read something from neighboring wires, from something that's creating noise in your household, and when you switch to low C, you really filter that out and get the real reading. So that might be very helpful. So that's it for voltage measurement. Let's look at how you measure current. So let's talk about measuring current. When you measure current in a circuit, in contrast to the voltage measurement where you place the voltmeter in parallel to the voltage that you measure, you need to place your meter in series with the current that you measure. So when you want to measure the current consumption of the circuit here, you place your multimeter in series between the battery and the actual circuit. So for our evaluation board, this means that you either take one of the power supply wires, remove it from the power supply, place it onto one of the amp meter connectors here on your circuit board, and connect the other wire then to your power supply, so the meter is in series here. Or you can use special connectors. So the designers of this evaluation board here were very nice to us. They added this jumper here with this pin header here, which we can use to connect our multimeter and measure current consumptions. So first we switch to the current measurement range. We take our measurement lead and place it into the amp connector. So that's the one here. You cannot really read this, I think, but that's the connector for amp. So you see here it's for ohms, volt, capacity and diodes. We'll take this one here. We connect this connector to one pin. And we connect this one to the other pin. We see it already turns on, and we already can see how much current this actually draws. We can check whether this changes actually something. That's interesting, that whenever I put this trim pot to its it does not actually change anything here. But there is a place in here where the current consumption actually rises. So that's interesting. You probably could check in the circuit why this actually happens. Whether this is because these LEDs here now run faster. Oh yeah, you see one LED here is on, and there are more LEDs than it really increases the power consumption. So that's very handy. Again, here for this multimeter, it will switch between the ranges by using relays. On a handheld multimeter, you have different sockets here. One usually for milliamp and microamp range, one for the amp range, and then you have the range switch which you need to select. That's something that this meter will do automatically for all ranges. For this one here, you need to decide beforehand whether you want to measure more the microamps or milliamps range, or if you go to the amps range, you actually need to change to a different socket. So that's important to keep in mind, because it will break the connection between your circuit, or wherever you connected your amp meter to in your circuit. You will lose connection there, which might change the functionality, or as in our case, where we measure the power consumption of the circuit, when we change something here, and this would I would need to switch the socket here, the circuit actually turns off. Yeah, so you have this one here. I already mentioned that you need to check for your burden voltage of your multimeter, so depending on the range you are in and the actual current that's flowing, the voltage on your circuit will be reduced, because the amp meter is basically just a resistor for measurement, and depending on the current that's flowing, the voltage over this resistor changes, so it might also change the functionality of the circuit, depending on how it actually works. So that's something to keep in mind, especially when you are working with low power circuits that are powered from batteries. You might come into a situation where your device just gets not enough voltage to function correctly. Something you also should be careful with are overcurrents. This meter here has just one input jack with one fuse of 10 amps. Most handheld multimeters have different inputs for milliamps and amps range, and they are usually with different fuses, and you especially should make sure that when you use the milliamp range that you do not put a too high current into it, because it will just blow the fuse. Yeah, you can change it, but it's something that you don't see. You don't see that the fuse has blown, you just recognize nothing is working anymore, and that might be strange. One thing or one strategy that you can use when you do not want to disconnect your circuit here is you can actually switch to a fixed range here, and then when you reduce the consumption here, even if it would go lower, you could still say, yeah, if it's just 100 microamps, I can still read 3 digits of current. This might be very helpful when you want to measure a higher range of currents, like normal operation and sleep mode, because if you want to switch between milliamps and microamps, usually it involves disconnecting the circuit, and then you will use your sleep mode. But if you have enough digits here, you can just use one range and get at least a feeling of how much current consumption in sleep mode actually is. So next part will be measuring resistances. So measuring resistance is relatively simple, because it just means taking your test leads, connecting a resistor, switch to resistance mode, and you get the value of your resistor. That's quite simple, nothing you can do wrong here. So basically that's it. There are 2 things to keep in mind though. One is you cannot really measure resistance for any device that's in a circuit. While you might actually get a connection for resistors here, like that, what normally happens is that that the voltage that the multimeter uses for actually measuring the resistance here might turn on like transistors, diodes, or even circuits here, which will then influence your measurement. So when you try to measure a resistor here, you would need an ohm meter that works with very low voltages, let's say below half a volt, to avoid turning on any semiconductor devices here. So usually just don't do it. The second thing to keep in mind is that the lower your resistance here gets, the more influence the resistance of your connectors, your probes and your wires have. For a 2 kilo ohm resistor like that, if this is 1 additional ohm, this does not really matter. I think this one here has an accuracy of 1%, which would be 20 ohms, so 1 additional ohm is basically within specifications. But if you measure, for example, this resistor here, which is a 1 ohm resistor, also with 10%, with 1% accuracy, and it reads 1.22. So it's 20% off, and that's probably wrong. So what you do here is you connect your probes to one end, and now you are measuring a 0 ohm resistor, basically just a wire, and you say, oh, yeah, it's 0.22 ohm. That's where this relative mode comes in handy, because it means 0 out this one here. When I now connect my resistor, I can read, yeah, it's 1 ohm, basically spot on. So that's what you want to do. If you do not always want to zero out, because you might have problems with the leads here, they might be corroded or something like that, so your zero resistance might vary over time or for each device. You can use what's called so-called Kelvin connections, and this is something that usually only bench multimeters have. So they not only have these two checks here for ohms measurement, they also have a so-called sense wire, which you can use for measuring with 4 wires. And what it will do is, if I connect this here, so one pair of the wires, that's this one here, will apply the voltage to your device under test. Yeah. And the other one will be used for reading, which means that any... Don't come loose here. Wow. No, it's still a bit off, so I probably should calibrate that one. Oh, I still have this rail mode on. Turn it off, and I need to switch to 4-wire mode, and it's 1.02. Not really within specification, but close enough. So one of these wires will place voltage and therefore current through this resistor, and the other pairs of wire will read the actual voltage here right at the connection, which means that any resistance that you have in your wires that supply the currents do not really matter, because they cannot affect the measurement, and the wires used for measuring will have no current flowing, so whatever their resistance is also does not matter. And that's a very handy functionality. As I said, handheld multimeters usually do not have that, because they just do not have place for so much input checks. So if you measure low resistance, then keep in mind, get a pair of Kelvin probes and use 4-wire measurement for your resistance. So measuring capacity is basically the same. You just connect your capacitor to your inputs. Again, you can see even if there is nothing connected, you already get some measurements. Come on. If I add my probes here, this gets even higher, because even just these cables have their internal capacitance. So if you measure small values, again you will use relative mode to zero out any of these. Again, be careful when you measure capacity that's in a circuit. It's much better to use a specific device for that, because they use much lower voltages. And also when you connect the capacitor, make sure it's discharged properly. half a volt probably does not matter, but if you have something that might have 10 volts or so on it, discharge it beforehand, because you might actually destroy the input circuitry of your meter. So this concludes my tutorial on how to use a multimeter. I hope you enjoyed it, learned something useful, and now feel more confident in using a multimeter and measuring your circuits. Thank you.